Okay, I had realized, I was interested, I've had quite a few people ask me during the course of the last 2 days about this particular little construction, and I realized there was one thing I just neglected to write down that maybe made it unclear, so I thought I would review it one more time. This had to do with the prescription, the absolutely least electrical engineering prescription about how you describe the dynamics of these superconducting electric circuits, which have to do with the case where you pass a magnetic flux through one of the loops of the circuit graph. An electrical engineer looking at that and saying this is a constant magnetic flux would say, you're dumb, there's no effect. But we're smart, I guess, or I don't know what. But because these are superconductors, it does have an effect, and I emphasize that in that case, leads you to all sorts of, in fact, or potentially many gauge-dependent choices about how you're going to represent it. But it must always be represented by these strings of vector potential. But it's up to you where to put those strings in order that the gauge invariant quantity, namely the line integral around the flux tube, is what it should be. And what I'd neglected to do is write down. I wrote down one of these terms. And I forgot, maybe it wasn't clear. And I said this was gauge invariant, and it doesn't look at all gauge invariant. But in fact, it's true that any one of these terms is gauge dependent. The only thing that's gauge invariant is, the effect of any physical prediction you make from the Hamiltonian in which you add in every single term. Which will in general include various interesting factors. So here's the example where I've split this vector potential alpha and 1 minus alpha in this loop, but then I have to pass into this loop, and this alpha phi external has to be further split, and I give it a beta 1 minus beta split. So that's a legal, or any choice of alpha and beta, any real number will lead you to some apparently different potential, but in fact always with the same physics, because it is only a difference of a gauge choice. Okay, so I'm going to return to the transmons and the resonators. Any further questions at the moment? No, okay, so I'm going to continue with a picture or some thoughts that I began with last time. I had these sketches, and I had some interesting factor of 10 wrong that got fixed. Recall that we have, on several different length scales, we have first a Josephson junction. Remember I said I'm zooming way out. So there's my Josephson junction. Graham missed it. It's 1 pixel. Because I want the scale of this picture to be such that the transmon itself is some pretty small thing. The Josephson junction and a little capacitor, but this is already, a significant fraction of a millimeter. And then a way bigger structure, several centimeters worth of an electrical structure, an electrical resonator, coplanar waveguide. And that's a big sheet of metal with some slots cut in it. And this part can go on a long way, but the idea is this has to end somewhere, or should end somewhere if this is going to be a cavity. Now I'm going to write an electric circuit that we use conventionally to model this, but I'm not going to just write the circuit down. I'm actually going to kind of, quote, derive it. And this is the concept of the black box modeling. This phrase, the black box quantization, BBQ, is a famous or a popular one introduced by a paper by the Yale group, Nig and co-authors. I separate the two thoughts. I don't jump immediately to the quantum part or the quantization part because there's already a non-trivial observation just about modeling. It's consistent with my philosophy that you should do as much on the classical side as possible before you're ready to quantize. So the question will be, I'm going to use my toolkit that I introduced last time, inductors and capacitors, to describe this, but I say, well, where are the capacitors? Where are the inductors? It's just some, metal thing. So for this, you need a couple of theorems from electrical engineering. I think Bell Labs 1920s, actually.
Can you just the little structure inside, I've forgotten what it consists of.
Okay, so we'll do one of these blow-ups. So, and there are only two options of what it might be. So here we zoom in on this submicron structure. And, well, depending on how you want to do it, what I mean by it probably is just this.
With a capacitor, right?
Well, with its own minute additional capacitance, you might say. But the idea is, if you only had that capacitance, this wouldn't be a transmon. Another way to say it is that the capacitance of this, millimeter scale structure is 100 or 1,000 times bigger. So it by far dominates the capacitance, and I can pretty well neglect the fact that this has a capacitance. And so at the theoretical physics level, it's just the cosine, EJ cosine. Of course, it itself means this metal structure that has like this and like that, and I spent the whole morning at NIST this morning actually talking about how they grow this and all that business. But these are, tens or hundreds of nanometer scale, but theoretically described by this or this. And then with the possibility of a magnetic flux pass through here, and that makes this a tunable transmon. I won't distinguish that for our purpose today. Okay, so I want to be able to describe this. I mean, this we call a resonator, and we will get to the point that, it's a resonator with some wave on it. It's a wave of what? Most of you know, but I'll review it shortly. But I'm going to make up a model which only has a few capacitors and inductors to describe all this stuff. And the question is, how do you get that? And I'll get to a point where I'll say, and here's the capacitor. And you say, what capacitor? All I see is a lot of metal and, deposited on dielectrics and things like that. And this is where we invoke the black box idea, which in this case goes as follows. We focus on these 2 points of space, which, remember, are just like 1 pixel on this diagram. And the black box is sort of inverted. That is, you say it, well, let me make a first sketch of what I mean by that, or what I have in mind. I have this, then I have this, and now it's looking outward. The black box is everything except this. And what I mean is that there is some response in the usual electrical engineering sense of this rest of the world. Now we can call it, for example, Z of omega, which emphasizes a few points about it, that it is a linear, so we'll make an approximation or an assumption that it's a linear system. And the point being, it's described by laws of electrodynamics, by Maxwell's equations, with only linear media. So that'll be the premise. So linearity. And then, but what we mean by the linear response, we have only 2 quantities. Classically, we have the voltage. We can put a ground here for the moment, but so there's a voltage here, and that causes there to be a current, a linear response current. So we would write, or the meaning of this, you might say Green's function, this sort of discrete Green's function, is that z times v, z of omega times v of omega is I of omega. Whoops, am I doing it the wrong way? V of omega, I of omega. So it's the linear response coefficient, and because it's linear, I can go to the linear and time invariant. Right. I can go to the frequency domain. And everything that you can possibly need to know about all this metal stuff is incorporated in this one function, this one scalar function. That's the idea. Now, we will further, or to make further progress, we will also assume that this is lossless. Now, I'll come back to that. this is supposed to describe the whole universe. And so, well, my whole universe will not be lossless, but out a goodly ways. That is, these will all be superconductors, and we will say the lossiness of the dielectric that it's sitting on is very small. And so any loss that we really have is way, way off the chip, so to speak, or way far outside this cavity. So we'll only deal with that later. So this is lossless. So linear, time invariant, lossless, and that gives a z of omega, but a z of omega of a particular form. And this is what Foster said in, I don't know, I'll say 1924, but I'm not quite sure of that, plus or minus a couple of years. He observed a series of facts, and it seems like all of them together are considered the Foster theorem. One is that the if z is lossless, then of course it only has an imaginary part, im z of omega, as a function of omega, and it will consist of a series of simple poles with positive residues, I guess you would say, possibly infinitely many of them, but generically they're simple poles. And also, I mean, it goes along with the fact that the slope of this function is always positive. So that's a possible sketch of this function. It turns out that the inverse of this, im 1 over z, otherwise known as im y, y being the admittance, so just the linear response expressed in the opposite way, all have this same analytic structure. They are not obviously identical functions, but it turns out the inverse of this function has the same properties of having simple poles, always positive slope. Okay, but then really the main content of Foster's theorem is that there is, resulting from that, a simple exact representation, actually two alternative exact representations of the impedance, and it's often called Foster 1 and Foster 2, or first form, second form. First Foster form is this, so LC circuits all the way. So potentially infinitely many of such LC stages, and that this is also a unique representation. That is, there's a unique choice of the L's and the C's that will give this. There are just some special cases. You have to be aware that sometimes, this is only a comment about the first couple of stages, sometimes you have a degenerate first stage, which is only a capacitor or only an inductor, or you maybe have possibly both. So the beginning may lead off with these, but it will then continue with an infinite number of simple LC parallel circuits. So this is Foster 1, and Foster 2 is a kind of dual representation. Oops, that loses that. Okay, I'll bring it back though. Foster 2 is a more kind of parallel representation. But this too, once you've decided on this topology of the circuit, is also unique. So no matter how complex the structure is, distributed conductors and dielectrics here and there, as long as it's lossless, it can always be represented by one of these two canonical forms.
So like representing analytical function by some.
Yes, it's indeed an observation that it's, since it has simple poles on the axis, then you have a partial fraction representation of that, and then each term in that expansion is representable exactly as an LC circuit. It's also a kind of diagonalization. Well, I don't know if I'll say it. This is more associated with the Z because there's a simple relation between each of these sections and the poles of Z, whereas in this case it's a correspondence to the poles of Y, the admittance. All right, so we're kind of close. That is, we'd say, well, our actual circuit is this. That's still not quite what I want to do, although that could be the story. That is, it says, good, that's the electric circuit of the Josephson junction with the transmon capacitor around it, and then with all the other stuff around it. that turns out not to be the most informative use of this Foster 1-2. And so to describe what we consider sort of a good or a best representation of this circuit, best sort of minimal approximate representation, it's best to actually mix these two. And so let me show you how you do that. Because you're actually allowed to alternate back and forth between these two different forms if you feel like. And we do feel like for the purpose of capturing the physics of this. So first off, if we first examine Foster 2, it will be likely, given the setup, the physical setup of this, that it's a little bit more like this. Now I'm doing something that has no particular mathematical meaning, but it has a good sort of pictorial meaning. That is, there will be an important, a significant sort of first stage of this second Foster representation, which is almost purely a capacitor, and a nice big one, and all further stages are small. So that's something one would have to confirm, but it is in fact the case, and it's part of the idea of having a distinct, discrete transmon. That the transmon should be something. Remember, we are going to have this attached to the white part of our world, which is just only one Josephson junction. So this is already what we've had in mind as our transmon. The only difference is that generically there is an inductance here as well, but it's really teeny. So it is indeed a fair approximation to not put it in, but it has a unique value. That is, for any given metal structure, you can calculate. You determine your analytic function, you fit it, or you decompose it into poles. You find a pole that corresponds to this, and so there's no ambiguity about these parameters. However, this capacitance may not really be exactly the geometric capacitance of this exact structure in isolation, but that's fine. It's sort of a potentially renormalized value. Okay, so we've done Foster 2 to get this far, but I want to do something else which reflects another physical fact of this circuit. So far so good. Now the remainder of this is itself an impedance, so it has again a Foster representation. Let's switch to this representation. What I will claim is that a feature of this is that it will in fact have this degenerate stage, for the simple reason that there's no DC current path passing from one side of the junction to the other. That's the point of this. There are breaks in the conductors, there are insulators, and no tunneling, by the way, from here to here or here to here. So that tells us that, but one again could confirm it by a humongous electromagnetic calculation and calculation of the remaining impedance function, and then getting the poles of it, and you'd find the first one has this degenerate structure. And then the rest are indeed this, but let's sketch a few more of them. But I'm already sort of demoting them in importance, because there will indeed be infinitely many of these generically. And certainly if I will get to a point where I shouldn't really only use Maxwell's equations, of course, but if I take Maxwell's equations seriously, then I will certainly have infinitely many poles. But this is where the next step is to recognize that for one of two reasons, only one of these really matter. Well, at least to good approximation. Now, I halted myself because, in fact, now we're seeing plenty of cases where it's really wise and important to keep more of these stages, to acknowledge that this really has a multi-mode character, that we're not only interested in, one particular electromagnetic mode, but it's a really good start. And you really, you make your choice based on, I sketched one field pattern, and what I mean by field pattern is, the pattern of electric fields, and I'm thinking of how to nicely draw it, but I drew the pink line, which would be, say, the strength of the transverse electric field in this particular mode. But it happens to be a mode in which I fit, one full wavelength into this structure, and I'm respecting a boundary condition which is a no current boundary condition. So that's why I have a zero derivative electric potential. So this is V of Z now, Z along here. And this is, well, in this example, I guess, this is in fact the lowest lying mode, but there are cases where, for not very deep reasons, sometimes you pick the second, the second harmonic, the second mode of this. But that's chosen by saying you have a pole here somewhere, and by design you make sure that the qubit frequency, omega q, in the sense of omega 0, 1 of the transmon, is pretty close to one of these poles and not so close to others. So that will determine which of these sections, which of these LC sections you will choose to retain. And so the useful first approximation is just to get rid of the rest of these. But you don't have to. I mean, and there are cases where, and we have actually models where you really have to keep two modes or perhaps more. And well, I know of experiments, Andrew Houck at Princeton has done experiments where you really had better keep 30 modes in order to describe the physics that he's studied. But for, the designs of quantum computers, for the engineering of quantum computers, people are pretty focused on getting this single mode approximation to be appropriate. Good. So I wanted to say all of those words so that I would get to this model and give these a few symbols. I think I'll write it over again. Because to me, often these lectures, I mean, I've actually been to summer schools where you just write this immediately. And you say, well, why? Well, it's got to be right. But then the next question would be, well, what's C sub r? Point to where's that capacitor C sub r? And now you hopefully understand you don't have to answer that question. It's a mathematical fit quantity, and it doesn't have to correspond to any particular capacitance of the physical structure. Nevertheless, it's a rigorous exact number in the sense that this fit is exact. I mean, under the conditions that I've stated, lossless and so forth. Now, there will be a rule of thumb for it, I should say, that this C sub r will pretty much be the following, but special to these 1D resonator structures. See here I've got a parallel plate capacitor, and you might be tempted, well, there's sort of two of them in parallel from this center conductor to ground. And you might say, well, that's the capacitance. And that would be wrong, but it would be correct in that it's one factor that determines the capacitance. It is approximately equal to the geometric center to ground capacitance, what I've just said, times something else. So this whole long thing, but then it's times this mode function. Well, normalized in some way. But anyway, that it's a maximum at the ends for this mode, but it's actually 0 in the middle. So, so it is in fact determined by the strength of the sort of the local electric field of this mode at the point where the transmon is. So that says it's not just a geometric, or it's not just the asimple capacitive geometric quantity. It inherits knowledge about this finite frequency, high frequency mode pattern, but that's only approximate. What it is really is this. It's really do the electromagnetics, do the Foster theorem, do this fit, and then to very good approximation you've got what you should really call C sub r, and then also L sub r. The product is the less ambiguous thing because you know that this resonator has a certain frequency, and that's got to be given by 1 over the square root of L sub r times C sub r. Okay, so let's in fact talk about the quantization of that model. And this is where we'll get to, I believe, probably onto pretty familiar ground for at least many of you, because now we'll get to say about Jaynes-Cummings models and about dispersive regime and dispersive measurements and things like that. So let me get on to those things. So let me re-sketch this model. So now we're back to, we don't need Blackbox anymore, but it got us where we wanted to be. This will be ground. I'm actually going to add, for a moment, I'll add a little bit more to this model because, but this is only ad hoc in the following, that it won't be, derivable from a Foster theorem. It comes from the following ad hoc consideration, that typically this conductor ends, but then it starts again, and you start afresh, and there's really a transmission line that continues, goes, say, to the edge of the chip, and then it's connected to whatever, your wires and your amplifiers and all that kind of stuff. And there is a capacitance here, from here to here, which we will give a phenomenological value. I mean, actually, you can also compute this. We'll call it C sub kappa. And some of you will know why I use the symbol kappa, because it has to do, in fact, with coupling to the outside world, including losses, finally. So what I want to add to this, but we won't do very much with this, but you need to think a lot harder about this once you do characterization of measurement and amplification, things like that. So there'll be these C sub kappas, and I've done a two-sided case. You can have things where you only couple on one side, but I'm doing the more traditional, or I mean, all the original experiments had the C sub kappa on both sides. And then what do I put outside? Well, I don't know, that depends, but I will certainly do the following. I'll certainly put a resistor finally, and I will, but one would put much more maybe, but in fact you have to recognize this is actually where the drive signals come from also. So you have a 50 ohm source here, which is actually what the, the box in the laboratory, you see the front panel, and it'll have a coaxial thing where you can connect in, and it'll say 50 ohms. And so this is part of what it means, that this is in fact 50 ohms in this model. But there's way more you could put in this model. And I'll add a little bit. I would claim that if you go a little bit further out, or somewhere in here is non-reciprocity typically. So it's sort of on the edge of where we want to do quantum mechanics, but not far over the edge. And the 50 ohms, I was reminded to say by talking with John Preskill about black holes, that this 50 ohms is, of course, a very close relative of the fundamental constant 377 ohms. I suspect half of you know this story, but it's always worth revisiting it, that the engineering number 50 ohms is what it is because it's not very far from what it, quote, wants to be, which is for waves in vacuum it would be 377 ohms. But, well, I don't know, it's better, this comes from a standardization, and actually there are 75 ohm systems. But it couldn't be millions of ohms, or it couldn't be, a micro ohm. The nature, our medium for carrying electromagnetic waves wouldn't want to have such a different impedance. So these are typically 50 ohms. However, you note 50 ohms is never seen by the qubit, and that's really important. If you put 50 ohms here, you could forget having qubits, and in fact, that's sort of the regime of critical damping of the electric circuit, so that's surely not a good regime for having a nice coherent circuit. So you work really hard to not having 50 ohms anywhere near the sample, and you make sure you put big blocking capacitances between this device and the outside world. And so for that reason, we will, again, in our quantization, we won't go any further than this. But reminding ourselves that this stuff's out here, including this crucial part of, you say, well, how do I drive this? Well, I drive it through this mean thing. The only way I get 1 qubit gates and 2 qubit gates is by energizing, by applying AC voltages way out here. And they have to sort of get down. If you will do models where that's stuck right here, but that's only, by following constants, its effect has been filtered through all this stuff. And so you only put it here as an approximation. Okay, so let me proceed and write the quantization of this. I don't want to be too lengthy about this because I would suspect that many of you have gone through this exact exercise. So I have this C subcoupling, C alone for the transmon. I have the E sub j. This is C sub r, L sub r. Okay, so the Hamiltonian will be the usual q sub r squared over 2c sub r plus phi sub r squared over 2l sub r. Those are very familiar terms. Plus, actually, let me do the Josephson next. Minus e sub j cosine phi plus, and now there's 4e sub c. I write e sub c, but, well, I'm working in the approximation where c is much greater than c sub c, and that will show up here in that I don't make a distinction. I mean, this subscript c maybe literally refers only to this c, but it's not correct, that it should incorporate a combination of these, which really comes from inverting a capacitance matrix. I might note just a couple of formal things about this. I have a 2-node circuit, according to my rules, or 2 dynamical degrees of freedom, and here they are, phi sub r and this lowercase phi. And the capacitance matrix is, I can kind of read it off, this node capacitance matrix. It has 2 capacitors going to ground, C sub R and C. And then that has the C sub C, which couples the 2 nodes. And that means I get to enter it 4 times, C sub C, excuse me. And then C sub C on the diagonal, and then minus C sub C here, and that's the exact capacitance matrix. And we have to invert this in order to really give the parameters in the Hamiltonian. But by writing what I've written here, I'm doing an approximate inverse of this, which is only valid in this limit. So I'm doing an approximate, or you might say a perturbative inverse. Now I write this in a way it's been written this way various times. N, I could hat everything. N is the conjugate variable to phi. And then I would have usually an N offset, and I'll write it that way because it's informative to think of it that way. But I've put a hat over it now because it's not that there's a classical offset, but I can say there's kind of a quantum offset. So I'll put another operator here, which I'll call V, the voltage, and then I can write what I mean by N offset. I just use a few circuit laws. So so this is the charge. I might say 2e times this, or I'll put the 1 over 2e here. So this is the charge at this node. And that's related to the operator V via capacitance, C sub CV. This is just a circuit law, Q equals CV. Yes?
So in the first term, when you had written Q square over 2CR,
Mm-hmm.
is that just the CR on the left in the circuit? Or where does the inverse of the capacitance matrix?
Well, it will come in the way you would do this really properly in the case where these there was no small parameter. You would invert this, and then each of the the 1,1 component of the inverse would appear here rather than C sub r alone. The 2,2 component of the inverse would appear here as a coefficient of the n squared. And what I'm about to, by kind of hand waving, give you what you would get for the 1,2 component, which will involve the operator, the product of these 2 operators, the Q1, Q on this node times the Q on that node, or the N on this node times the N on that node. Does that clarify?
Also, I didn't get what you were saying
That's a supplementary. Okay, if you've forgotten that, how many people know what are the fundamental constants that give you 377 ohms? Yes. Okay, mu naught, epsilon naught. What do I do with them? Very good. That's indeed. Yeah, there you go. Square root, I believe, right? Must be square root. Yeah, so that's ohms, and that's 377 point blah 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 ohms, a fundamental constant of nature, known to well, okay, I'll tell this story. It's presently known to like 15 decimal places, which is not so impressive when you if you know a couple of years ago it was known to infinitely many decimal places because it used to define the ohm, but it doesn't anymore. The h bar has one. So what defines the ohm presently is the von Klitzing constant, and you have to know the fine structure constant to get this number. So you have to measure the fine structure constant to know the impedance of space. Okay, back to my more prosaic derivation. So I claim that this n offset should be thought of as this quantity, and then I will put in let's see, how do I do this? Oh yes, I have to relate this voltage to this to the charge operator here. So I will write C sub C over 2e, and then this has to bring in C sub r, Q sub r. If you don't like these hand-waving statements, you can exactly follow the prescriptions that I gave you, the axiomatic prescriptions, and you will get this except way longer, and then you have to say, oh, well, but I have to be smart and use the fact that C sub C is small and maybe do a Taylor expansion, and then you'll get to these results. I finished, however, with the hand-waving. That is, if you permit me to say that the operator that appears here is Q sub r, then you will note that I will now have coupling terms. I guess I'll rewrite this also C sub C over C sub r n sub r. So that's indeed the Cooper pair number operator on this node. And then let me proceed. I'll drift over to here. The thing you should note is that we do in fact have a coupling term. And it will be, well, minus 8 e sub c n times n offset. That is, you get this by multiplying out the square present here. And let me quickly kind of get to the answer. I will switch to second quantization partially, in the sense that I will immediately recognize, yes, this is just a harmonic oscillator. So I certainly want to represent that by writing this, omega r a dagger a. So the creation and annihilation operators of the excitations of this part of the circuit. So that's the number operator, the number of photons, indeed, living in this resonant mode. Then we have a qubit, and I'll immediately write down the absolute most stripped down formula for that qubit. So you recognize I've gone to a two-level approximation and just retained the fact that there is some 0-1 splitting, and that is, to reasonable approximation, a formula that I've already given for just this part of the circuit alone, the transmon part. And then the interesting part is the coupling. And then there's I'll say a few words about G, but we have A dagger sigma minus plus A sigma plus. This has also involved a rotating wave approximation. I would have more properly had 4 such terms, and I need arguments which I will not develop in these few minutes for why I throw away those 2 terms. I bet 80% of you have done that at some point in lectures or in courses. Okay, and then this G, I wonder if I have it written down here. It's a moderately complicated combination of all the parameters. I know I had it written, but I fear that it's written somewhere else. I'll tell you what it does contain, certainly. It contains, it's proportional to C sub c, but it also has factors like this. E sub, now this is where be helpful if I knew which way it is. E sub c over E sub j to the 1/4 power, and then a corresponding factor, E sub c sub r over E sub, I'll call it L sub r to the 1/4 power. There are some more factors. It has to get finally dimensions of energy. So I'm sorry, I had that written. I'm sure it's somewhere under my hand, but I didn't bring it up to the front. Maybe that's enough to know about it. Okay, but so this is the Jaynes-Cummings model. And so the next few comments that I would make about this are the same you would hear in a standard quantum optics lecture. But the most important thing is to say that this is a very versatile setting for control of a quantum state and controlling a qubit. So let me run through a few of those fairly standard facts. Let's see, which of these things do I want to do? I guess one thing that's maybe nice to know is that this, if you haven't seen this, is that this, especially once I've made this rotating wave approximation, is a trivial quantum Hamiltonian. That is, I can immediately exactly diagonalize it. And I don't think I was taught that the first time I saw this model, so let me make sure that none of you are left in that particular style of ignorance. Oh, okay. Let me not use the wet version. So, and the way I like to think of this, the triviality of this Hamiltonian is to just imagine writing the whole matrix representing this Hamiltonian. So that's, of course, rather laborious because the matrix is of infinite dimension. But let's start from the bottom. So we start, I'm going to write here quantum numbers. This will be the photon quantum number, and this will be the qubit. So this number has to go to infinity, but I just alternate from 0 to 1 for the qubit. And now the photon is 0 or 1 or 2 or 3, etc. And now the now I realize in what I've sketched here, I'm about to really shift the scale of energy. Recall this. Let me promote this to. Let me shift this whole thing by a constant. 1/2 times identity. That's just so I can call the ground state energy 0. That's the only reason why I stick that constant in. So 0. Did I get that right? I think so. 1. Yeah, sorry. I forgot there's already a 1/2 outside. So that's 0. And this has no matrix element to anything else. So I've already diagonalized one part of this Hamiltonian. Its ground state is unaffected, and the ground eigenvector is exactly 0, 0. Its energy is exactly 0. Then I get to here. Now I have omega 0, 1 on the here, and I have omega r here. That's either we have one excitation of the qubit or we have one excitation of the resonator. And these are connected, and this here I enter G. And that's it for this block. That is, this doesn't couple, there are no other matrix elements involving G to anything else. And then I get to the next block, which is well, it has one more quantum of, let's see, have I lined this up correctly? 0, 0, yes. I have next, I'm now in the 2 quantum sector, 2 quanta of excitations, either for the photon or the qubit. So I write on the diagonal omega 0, 1 plus omega r, 2 omega r. And then this is g, but not g, square root of 2g. From the ladder operator matrix element rules, and that's again its own block. So this in fact decomposes into a set of 2 by 2 blocks, or in other words of saying, another thing to say is that it commutes with the total number of excitations, of number of qubit excitations, number of quanta in the qubit, plus the number of quanta in the resonator. So any of you can diagonalize these blocks, so you're finished, so you know the spectrum. But it's maybe worth it to know, I mean, you can just diagonalize these perturbatively. So let's do that in this block. So perturbative diagonalization. So I can just do this by I. Omega 0, 1, I will introduce a constant here, which is, well, I'll introduce in a moment. Omega minus g squared over big delta being defined as omega r minus omega 0, 1. Let's consider that to be positive, although it works either way. So that's one part of this, and then diagonalizing this part, omega r plus this, g squared over delta. So and that's already quite good for many purposes. This has its own name in this subject. This g squared over delta parameter is chi, so it's the dispersive shift parameter. And to understand why it's called that, it's best to know, well, I do want to state that I'm doing this sort of ad hoc, unsystematic analysis, or beginning to do it, but you would rather quickly learn that there's something you should, or once you can figure out a better approach, where you can figure out a way of changing basis in a much more systematic way than just this ad hoc perturbation theory. And this goes under various names. It's just the, quote, canonical transformation, or the polaron transformation, or it fits a more general theoretical framework called the Schrieffer-Wolff transformation. Here I'll just call it canonical transformation. Because it'll be useful for explaining sort of the next step. The idea is to say, I'd like to diagonalize this Hamiltonian, at least exactly, and get a new, I'll call it effective Hamiltonian. And I get to the effective Hamiltonian by a unitary transformation on the Hamiltonian we have written here, there. And for somewhat historical, or I don't know why, notational reasons, you write it this way, and the generator of this unitary operator is written this way, meaning that this is an anti-unitary operator, s equals minus s dagger. That's just to save writing a lot of i's, so no deeper reason why it's done that way. And so there is indeed a way of deriving this, but I'm not going to do it. I'm just going to say that s, or a good choice of s that does a good job of partially diagonalizing, or first order diagonalizing this Hamiltonian, is the following: minus g over omega r minus omega 0, 1. And then this particular anti-Hermitian object, a dagger sigma minus minus a sigma plus. So it looks deceivingly like the g, like the Jaynes-Cummings coupling itself, but it crucially has a minus sign here, so it's really not the same object. And it's dimensionless, so it has an energy denominator. And then evaluating this, you get the observations that I just stated, but you actually get a new Hamiltonian. You get a new operator expression for the Hamiltonian, which which you could then finally infer if you did it by my matrix method, you would, at long last, you would finally get back to that. But it's best to just write it. So H effective turns out to be this. Let's see, make sure I collect all the terms correctly here. Yes, so there's omega 0, 1 over 2, but now plus g squared over delta, 2 delta, sigma z, plus omega r, but then plus, I'm frankly suspicious about my sign, so I feel standing here writing that there should be a minus somewhere here, but I'm definitely not going to diagnose it at this instant. Plus g squared over delta sigma z a dagger a. Okay, so I say that's a diagonalized form, and sure enough, each of these are, they're diagonal in the number basis or diagonal in the usual qubit basis, and this is a product of the two. So this is a fully diagonalized Hamiltonian. Observation?
Maybe that's when you refer to it there's a minus sign.
Yeah, it had its level repulsion or something, or mode repulsion. So I feel, I would feel on the basis of this that I'd like to put it here, and I'll kind of put it there with a question mark, because I'm really bad at doing minus signs on the fly, and somehow my note writing failed me, or I screwed up at the note writing time as well. So okay, but let me discuss the the physics of this. First of all, it says each of these gets a bit of a shift, so the qubit is a bit shifted in frequency, and the resonator is a bit shifted in frequency. It's got to be a minus sign. But the interesting and important thing is there's this new coupling. This, as I said, we call chi. So this is the dispersive shift, and the way to read it is that it can be read in several different ways, but the useful way to read it, in the sense of it leads immediately to an observation of how you measure this qubit, is that it's an additional shift of the resonator frequency, which is state dependent, which is qubit state dependent. So it either, if the qubit is a 1, it shifts the frequency up a bit, and if the qubit is a 0, it shifts it down a little bit. And this in fact provides the basis for how to measure this, which goes as follows. You interrogate this, you send a tone in at the nominal frequency of this resonator, which you know ahead of time or you've measured already. And you study, for example, its transmission properties, although it can actually be its reflection properties. Now, it will not actually be the resonant frequency of this resonator. It will be shifted up or down a little bit, depending on upon the state of the qubit. And therefore, the transmission properties, and in fact it will be the phase of the transmission properties, will reflect whether the qubit is a 0 or 1, or it will in fact measure whether it's a 0 or 1. So that's, I'm doing this rather quickly. So this is the basis of dispersive measurement. And it is indeed what's done all the time, in the IBM experience or something, that they have a resonator devoted only to, it's devoted to measurement, let me put it that way, and also to applying 1-qubit gates, applying gate tones. But there are separate resonators for every single qubit in the IBM 16-qubit experience. So one of their primary jobs is to do 0-1 measurements of each of those qubits. Okay, let me, now I can really quickly do at least a couple of versions of 2-qubit gates on the basis of exactly this story. And I'll do that by putting another transmon in this resonator. and investigating what new thing I will get from that. So now let me look at the 2-qubit Hamiltonian. And, well, I'm not going to draw any circuits or anything, but I basically will just say, or I'll go do it over here. I will get to the 2-qubit Hamiltonian by putting some sums here. I need two operators. It might possibly be an I-dependent, that is I equals 1, 2 for qubit. So this is the 2-qubit Jaynes-Cummings Hamiltonian. I need an I here, I need an I here. I do not need any new indices on the A, because the resonator is common to these two. I need a new black box theory. Maybe I won't discuss that, because now this has 2 ports rather than 1, two Josephson junctions rather than 1. But besides, or I won't get into that, I don't think, but let me also say that you can diagonalize this Hamiltonian by the same procedure. Where did I write it? I'm looking for my S operator. Here it is. So this is where it really pays off to have written this down, because the procedure for getting the new effective Hamiltonian is also to just add 2 of these generators. They're added in the exponent, notice. So I have a G sub I, I have omega 0 I, sigma minus I, sigma plus I. So now let me just quote you the answer. This turns out not to fully diagonalize the Hamiltonian in this case. You get some new types of terms. So I think it's worth writing. Nobody said that this was going to fully diagonalize the Hamiltonian, and in fact its main purpose, the main rationale for its construction, that is of this canonical transformation, is really to decouple the qubits from the resonator, but not from each other. So it doesn't succeed in fully diagonalizing within the qubit sector. Now in the original case there was only 1 qubit, but now we have 2 qubits, and we can expect something new, and we do get something insightful from the calculation, which of course I will only jump to the end of. So the H effective for 2 qubits we'll have all the terms that I've just stated. Well, I'll write them all out again. Okay, it's too boring to write. Okay, H effective 1 plus H effective 2. So I decided I won't write them, but they're just exactly these terms again, plus minus 1/2. Well, okay, I write the following, which is rather silly in this case. I is not equal to j. Of course, we only have 2 of them, so this is only one sum. But the point is, this works also if I put 3 resonators or 4 or whatever. It will give one resonator to another interaction, Gi, Gj. Some interesting combination of energy denominators, omega r minus omega j plus 1 over omega r minus omega I. And now the following operator, sigma I plus sigma j minus plus sigma I minus sigma j plus. Okay, so that's the end of the story. But that says that the presence of the resonators has induced this effective coupling between the 2 qubits. So in this field, this is all summarized as being a kind of exchange coupling. So this is a J coupling, exchange coupling, and it's of the flip-flop type. So, or another way of saying it is like the case, so I've erased it now, but I stated that there's a certain preservation or this conservation law of number of excitations, and that's still respected by this. That is, if one quantum is removed from the qubit I, it is added to qubit j. That's the that's the way of reading this. So there are sectors. There are symmetry sectors involving fixed numbers of excitations. It does mean that the sector 0, 0, 0, and I could just keep going on, the number of qubits, 10, if I do 16 qubits, all of those qubits in the 0 state is still the ground state, and it's still the tensor product of the zeros. But now there's a new insight, which I could have already mentioned before, that if I have an operator like sigma z, I don't know, 1, qubit 1, the 0 state as I've just said is still exactly literally the physical 0 state of that transmon, whereas the 1 state, and I'm going to state a new word here, is really a Wannier function. What do I mean by that? Now I want you to think of a whole collection of qubits. So here's a qubit, here's a qubit, here's a qubit, here's a qubit, there's some resonators. And suppose this, I'm referring to qubit 1. So here's qubit 1. And, well, poor choice. I have a lot of 1s here. Maybe I'll letter these. So there's A, there's qubit A, there's qubit B, there's qubit C, there's qubit D. And if I look at the sigma z operator of A, and I ask what is the meaning of its 1 state, it's actually a rather delocalized object. That is, it has some amplitude of being, the 1 in the original basis on A, but this 1 will have hopped around according to these, various terms that I've introduced here, for example, and now at the multi-qubit level here. So if you zoom out even further, you're doing your surface code with 8,000 qubits or something like that. It says that what you mean by a 1 of this qubit is really some kind of cloud, and I would also refer to it as a dressed state, that the 1 is only, localized to some approximation on that physical qubit, but there's an orthogonal state, that's why I call it a Wannier function. There's an orthogonal state on the neighboring qubit, similarly delocalized. And so that's the picture you should have in mind of what's really happening when you create a 1 state. It's actually creating a little cloud in this whole network. That's not actually so good necessarily. Yes?
I had a question about sort of what you were talking about just a moment ago before we got more than 2 qubits.
Mm-hmm.
So just in the 2 qubit case, when you have 2 junctions like you've drawn in the upper panel before, so do they have different omega r's in their sort of like Foster representation, or is it really
No, there's 1 omega r.
Okay.
Yeah, that's a good...
The point you made then earlier in the lecture about how the capacitance for that resonator is determined by a geometric capacitance from the center to ground, but it's also shaped by the mode profile.
Yeah.
So,
Yeah, now the simple rule of thumb is I've got a second transmon, it's at a different place in the mode profile, and that's its G. That's what its capacitance, I mean.
location in the resonator determines the coupling.
Physical location determines the coupling, yes.
Not CR, because they have the same CR.
Well, okay, now it depends on whether there's the C there's the C coupling, but then you get all the way to G eventually. G will then itself also depend on other parameters, because I sketched this, I didn't have this complete formula, but it has these kind of factors in it. So yes, it depends on factors of not only of the coupling structure, but also of the resonator itself. Yes, it does. Actually, that's a good transition. I'm now ready for my final section of my lecture. Yes.
So then the direct coupling be better, like the spectral qubits? I mean,
Yes, okay, so of course I've only done this one version of CQED where you put them on resonators, and which has the cool feature that you can have them centimeters apart, but they're still well coupled. But yes, it's true that like the Google approach is to put 2 qubits sort of right next to each other. that actually leads to the same effective coupling in the sense that it's still this flip-flop, or I-swap is another jargon for it. So the direct coupling, the capacitor-only coupling, also gives something of this form, but you have less control over this. This you can actually have of either sign, and that's actually of some use. In the direct capacitance way of doing it, you only get one sign. It's only, quote, positive. And that can be somewhat limiting. I mean, not for the sort of gate model approach, quantum computing. Yeah, sure. No, that aspect is independent of any details of this coefficient. It's just dependent on the fact that the effective coupling is of this form. Okay, so I promised that there was still something radically missing, actually, in circuit theory. And let me get into that, so that the word being reciprocity or non-reciprocity. Let me get into that by saying that there is, or one thing that's useful to know, there is a black box model, and there is a Foster theorem, although it's called Cowers theorem, for the many junction case. Sorry?
Sigma Z exchanges.
Sorry, what do you mean?
Sigma plus, sigma minus. To higher order, but yes, you can eventually get ZZ terms, but you have to go higher order in these G's to see such terms, such interaction terms. Oh, I did forget to mention, this is also the basis of doing 2-qubit gates, but there are a variety of ways of using this potentially entangling interaction to actually do entangling gates. I'll maybe mention only one of them. Sorry, I almost skipped by that without saying it. So let's do only one 2-qubit gate. You invoke tunability in the version that I'll just mention right now. If the 2-qubit frequencies, so here's on this axis is time, and here's omega qubit 1 A, and here's omega qubit B. And if you hold them apart, so if the difference between these is much greater than J, this interaction is, it's non-secular, or in a rotating wave approximation I can throw it away. There are several languages for it. But it has very little effect. It has little entangling power. But as a function of time, you tune one of these qubits and bring them into resonance with each other for a certain length of time, and then bring them apart again. Then during this interval of time, you imagine doing this, quote, adiabatically. During this interval of time, this J interaction, this flip-flop interaction, is capable of full entanglement. Let me leave it at that. I mean, one has to go longer analyses to really see that that's true. But this in fact gives the so-called I-swap gate. There are others that's how I-swap works. There's also the, I don't know if there's a simple name for it. I call it the DiCarlo method, which involves also causing tuning into an interaction, but a higher level interaction. And then there's the so-called cross-resonance or microwave-only method, which is the IBM and others method. They're all based on the presence of this interaction and interaction of this functional form. What's special about the IBM approach is it doesn't involve any of this adiabatic tuning. It involves only turning on and off tones, microwave frequency tones. Okay, but I keep saying I'm promising to get to something dramatically different. Let me first say that there is a kind of black box model for the case, which is sort of analogous to this. I say I have 2 Josephson junctions or more, or I even have, I should also maybe include in this signal generators. So this will be a 3-port black box situation in the sense that all the rest of this is black, but it's all the linear, time invariant, passive, I don't know what other things I said, electromagnetic environment. But there you get new ideas, or the this in electrical engineering, this is called a three-port situation. So you have two terminals in, two terminals in here, two terminals in here, and then there's an object which you describe not by a scalar function z, but by a 3x3 matrix of z coefficients, so linear response coefficients. And there is a Foster-like theorem for this, in which the key thing is, yes, there is a sequence of LC circuits, but you consider them hooked up in a quite different way. Again, infinitely many. But in here, what you do is you draw, well, here's port 1, the terminals of port 1. Here's the terminals of port 2, terminals of port 3. Let's stick with 2 ports. So this will be a 2-port, 3-pole model. And then what you stick in here are only transformers, it turns out. And it's the turns ratio of these transformers. There's a whole network of pairwise transformers, which in total is called a Belovich transformer. There's some beautifully well-written and rigorously done electrical engineering in a particular book, which I have loved for this subject, by Newcomb. Newcomb. Linear multi-port synthesis. This is pure electrical engineering, and it's very nicely done and beautifully rigorous and physically insightful. So those of you who think of this as your profession perhaps might be aware of this. This is from 1965, so it's not new news by any stretch of the imagination. But there you can find a description of this. And these transformers, they all have turns ratios, N, A, B or something. So the whole network of turns ratios. And they determine what you might call the participation ratio of this. Say this is the one resonator. This is somewhat getting to your question. Here's one resonator, and it's seen by each port. But the participation ratio of each port is different. That's the new physics language for this. The 50-year-old or 60-year-old electrical engineering language was simply that there are turns ratios of an effective transformer. And I've told you we also have effective ways of writing down the dynamics, or the, I should say, the constraints in the Lagrange procedure, Lagrange function procedure for this. So it's not scary, except it's wrong. This goes with the name of a famous electrical engineer of 100 years ago named Cauer. But shortly after his time, it was realized that this was inadequate for describing multi-port responses, and that this is restricted to the reciprocal case. But what about non-reciprocity? So what I want to do for a few minutes, I still have 15 minutes, and I'll be able to at least state the high points of this, of what is meant by non-reciprocity, what is an example of it, and how do we deal with it in our axiomatic Lagrangian theory, which is actually not so hard, but has turned out to raise some interesting subtleties, actually. So the counterexample is actually, or the thing that definitely cannot be represented by Foster or multiport Foster or anything like that, is something that indeed is sketched this way, and then you have some arrow like this, and this is a circulator. I think, well, maybe circulators are only well known to those of you who are really in the business, but if you're in the business of, running your lab, you better have one of these, or a lot of them, in fact. As I said, they're sort of on the frontier of where you would put your cut between quantum and classical, but they've in general been migrating inward. That is, they have been present in what you would really call the quantum part of the experiment in a few cases.
And from an ideal point of view, they really belong there. And so let me state what they are, axiomatically in several different ways. One way that it's stated is to ask what's the admittance matrix of this. So what that means is that I apply, remember admittance, I always have to think for a moment, YV, right. Admittance means I have currents, voltages applied, and I have current outputs. And the strange behavior of the circulator is the following, that if you apply a voltage here, so a voltage difference between these two terminals, but apply no voltage differences here, you nevertheless get current flows, which are of this character. Oops, I was trying to be careful with my arrows, so current goes in here and out there, basically. And these, indeed it's two-port, so the current flows back to ground here. But the way to write it as a matrix, which is easier than what I've just been saying, is the following. 0, G minus G. G will be a conductance, minus G, 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 0, 0, minus G. Okay, that's it. G is some conductance parameter, better be 1 over 50 ohms, actually, for good practice. And notice that this matrix is anti-symmetric. And so it's a theorem, it turns out, that if you fill the inside of this with inductors, capacitors, transformers, even resistors, even nonlinear inductors, anything you want, that this matrix response has to be symmetric. So that's the case of reciprocity. Now there's some sort of rough correspondence between the dichotomy reciprocal, non-reciprocal, and time reversal invariant, not time reversal invariant, but that's only an incomplete correspondence. It's a correct correspondence in the case of lossless circuits. But reciprocity or non-reciprocity is a good concept also for lossy circuits. So one should be warned not to associate the two too closely. Anyway, so this shows that there is something in the world that can't be represented by the toolkit that I've been describing, including a device of considerable interest. The thing that's actually of interest about this is more of its wave signal. This is sort of a DC description of what it does. But a more informative thing is to say what it does if a wave impinges on it. And wave means that it's it's a wave of voltage with an accompanying wave of current. So you need to know the S matrix. And the corresponding S matrix for this just has this simple form. And what this S matrix means is that if the signal comes in here, if energy comes in here, if the pointing vector enters here, it exits here. The wave exits here and does not get reflected. But if you send in a signal here, it does not retrace the path of this signal. It actually goes out this way. That's the meaning of this circulating arrow. So it's very valuable for signal handling. Now, let me say where this, or the way this is dealt with in theory, in the theoretical work, is to choose actually a simpler canonical device. And historically, the one I'm about to state was introduced first, and that's the one we'll quantize, or I should say make a Lagrangian for, state a Lagrangian for. And that will be the gyrator. Gyrator is, by definition, it's a conceptual device in the same way that, ideal capacitor, ideal inductor, ideal transformer. Here's a new object, has this symbol for it. Let me pause for a moment because I'm just curious. I mean, how many of you have ever seen this symbol? Okay, the two experimentalists in the back, so 3. Okay, so interesting. I would say that if there were any electrical engineering students here, they would say, "Oh, I saw that in freshman year." So it's interesting that, but it never gets into physics. Okay, so it's a 4-terminal device which has the following specifications. It's specified by an conductance, or equivalently by a resistance, but it has the following IV characteristics: I1 here, I2, and it will be kind of rather transformer-like. Let me ground the bottom. Here's V1 and V2. And then it says the following: I1 is equal to minus G V2, whereas I2 is plus G V1. So it's something that you pass a current through and it looks lossless. There's no voltage developed at that terminal, but there's a voltage developed at the opposite terminal, and vice versa, but it has this crucial anti-symmetry. Now, it's proved, in fact, that, and actually the larger part of this book is devoted to the axiom that this is complete. That is, that this object forms the basis of describing any non-reciprocal response in this black box sense, and therefore the non-reciprocal response of any circuit device. But I'm concerned mainly with, in these final minutes, in saying what consequences it has for our Lagrange theory. So now this, I've noticed, you can find in the engineering literature, but I've found it only in like 1 or 2 places. So this is relatively fresh news, even for the engineers. I will say, first of all, the things that, this was invented by a worker named Tellegen in 1948. He was a theorist who recognized the current deficiency in circuit theory. He noted, he was well known for so-called energy theorems, and he easily showed that this does not store any, it is lossless, he proved, and it stores no energy. So it stores neither electric nor magnetic energy. So that sounds like something, you don't know where to put it in the Lagrangian then. It's not a kinetic energy, not any energy. And so you might think it's a kind of constraint, but no, in fact, it's another term. It's something else. So let me just write it down for you. So remember, we're going to use phi's. This will fit right into our phi theories, our flux, node flux quantization scheme. And so the Lagrangian will be this, or is this, 1/2 G. I'm going to leave a little space here. Phi1, Phi2 dot, and then minus, leaving some space, Phi2, Phi1 dot. So you see it has a kind of anti-symmetry, and it has 1 power of the velocity and 1 power of the position, if you talk about mechanics. Now, in the longer version of this, I'll say this at the end. I mean, just take these coefficients to be 1, but I'll have a comment about them at the end. So this is not a familiar quantity. We'll add it to the Lagrangian. It involves a time derivative, so it's somehow belonging to the kinetic energy. Let me just cut the story short, since we're basically out of time, that this is the Lagrangian, in our particle analogy, this is the Lagrangian of a uniform magnetic field. Now this is again contributing further to our confusion of effective magnetic field and this and that. What I mean by this, to be more precise, is the following: that I have this, I have at least 2 variables in my dynamics, Phi1, Phi2. I might have Phi3, Phi4, whatever. And we've seen that inductors and Josephson junctions serve to produce potential energies. Say 2-dimensional, in this case, potential energies in this, and capacitances are just ordinary, kinetic energies. Define the mass basically, and this has the effect on the dynamics of having. Let me get another
color here, of putting in addition a time-independent magnetic field, uniform, across this phi 1, phi 2 plane. That's a new and interesting addition to it. It means we can get new kinds of effective dynamics in circuits that we couldn't otherwise get. For example, a famous circuit, Telegan introduces it in his first paper, is this. 2 capacitors, that's all. And normally, well, you'd say, well, there's nothing, a circuit with only capacitors is a strange one. You would have formally infinite frequencies, perhaps. But this turns out to have, so this is just the problem of the free particle in 2 dimensions in a magnetic field. So we know that various things about that. The motion of particles is cyclotron motion. So in fact, it is a kind of harmonic oscillator, and that corresponds to one of Telegan's theorems, which is that if you look into if you have a combination like this, a gyrator and a capacitor, that it's equivalent to an inductor. So we would say this is a resonant circuit. This is in fact the reason why it's taught to all electrical engineers, at least ones who are going to do integrated circuits, is that all integrated circuit designers hate capacitors, hate physical capacitors, and they love the fact that this can mimic if you have a gyrator, you can mimic the effect of an inductor with only capacitors, which are easy to make in integrated circuits. And then the other news is that this can be made not by simple means, but it actually can be made with a transistor circuit. So if you learn design of integrated circuits, you will learn the transistor gyrator, and you'll learn that that's the way you avoid ever having to introduce inductors in your integrated circuit. But here this is actually current research for me and my group. We're thinking about, okay, what could this insight be leading to? There are rather subtle questions about compactness, I can warn you, and that's what we've actually been studying quite recently. But it's nice that it's finally complete. I'll state what I was going to say. You can actually put an additional constant here and ask, maybe this is a modification of the gyrator, but it turns out it's another gauge parameter. And it reflects the usual, gauge freedom in defining or in describing a magnetic field with a vector potential. Yes.
So that's basically adding a total derivative to your Lagrangian, I think.
Well, yes. Okay. If you're a classical physicist, you observe quickly, as you just did, that this is the same as adding a total derivative. So you're not surprised that it doesn't have any effect. Now, if you're a more sophisticated quantum person, you say, well, okay, maybe there's something topological that you have to worry about, and that's sort of what we're into at the moment. We don't really know if we've got a final answer for that questions in that direction of whether this does or does not have any quantum effect in some circumstance. I might say that, the guys in the back know that there are definitely real gyrators and real circulators. They often achieve them by the means that I didn't touch on at all in these lectures, which is by parametric means, so by parametric modulation. So that subject I've left untouched, perhaps unfairly, because that's a huge subject currently in circuit QED, is what you can get by still lossless but time modulated circuits. The other comment is that there are passive circulators. They're in very common use, except they only work in certain bands. So this is very much an idealization to say that it has a certain scattering property independent of frequency. That's, I guess we'd love to have such devices, but we don't. And so real devices are a mixture of not mixture, but networks of ideal circulators or gyrators and regular, inductors, capacitors, which describe the actual frequency dependence. They seem to be pretty much like transformers in that no matter how hard you try thinking of ways you would actually make one, you can only think of approximations to them.
And I have the feeling that's some fundamental thing that you're taking a limit that electromagnetism doesn't really like. Okay, so that is circuit quantum electrodynamics, and I hope you'll remember some of this in the midst of all the other enormous piles of things that you're learning in these weeks. So thank you. Yes.
So those guys in the back were using the circulators mostly for isolation?
Yeah, typically. There is one fairly quantum-style experiment in the Berkeley group. They've used this to do measurements in an entangled basis by sending signals successively first to one qubit and then to another qubit and then out.
Yeah, that was going to be my question. Is there application beyond this?
Yeah, that's the application I know about. And other groups are trying to do, further extensions of that. You can do direct parity measurements, for example, if you have circulators, by doing sort of bounce, bounce, bounce schemes. Further questions? Yeah. Yeah, well, the way the professionals do it is by simulation, actually. But they have pretty high octane simulators for doing the electromagnetics of microwave frequency electromagnetics of quite complex 3D structures. That's kind of the recommended way of doing it. It's not that easy to measure, and it's actually not easy to measure the impedance looking out from the Josephson junction. Certainly not in any direct way. Well, I think to describe it quantum mechanically, you have to actually describe what are the fundamental degrees of freedom behind it. And so I don't know how to do it. I don't know how to go without some kind of intermediate representation where you've said something more about z of omega, like what it's due to. I know, but that's not quite true in the sense that there are cases where you do environment theory and you can relate some dynamical properties directly to z of omega, but that's often in the lossy case where you want to describe decay of the system. Then you refer directly to the real part of the z in the lossy case, and that in a rather direct way tells you things about T1 and T2 and things like that. But to describe really lossless dynamics, I don't know of an alternative to having some kind of discrete representation like Foster. This shows it's not unique, and they all have to yield the same dynamics, indeed. Including after quantization, yeah. Yes?
So if you have some time dependence, is this not valid anymore, the black box model?
Time dependence in the black box?
Yeah.
My 10-second answer is that is right, it's not valid anymore. And I need another half hour to think about that one.
How would you represent the rest of the circuit then?
Well, you couldn't go to the frequency domain is one thing. I don't know, your tools become limited. And then it depends a lot on what kind of time dependence. If you have one harmonic time dependence, then you have one set of techniques. Then you have parametric modulation techniques. More generally, I wouldn't know.